Hey guys, welcome to this video series on thermodynamics. Now, thermodynamics is a vast subject area within physics, and we, over the next several videos, are going to focus on a few of these areas. We're going to connect everything by about 3 different strands. The first is the transfer or the movement of energy. The second is the conservation of mass energy. And the third, and to me the most interesting, is the microscopic view of systems and how we can use statistical analysis to help create a wider understanding of a system as a whole. So in this video, we're going to introduce each of those strands from a basic standpoint before we really start to unpack them in the next several videos. We'll start by talking about how energy moves, or how energy is transferred between systems. Let's get into it. Now, the word thermodynamics, from a very basic standpoint, is really focusing on the idea of the movement of heat. Now, we focus on the word heat, but there's actually a lot more to that than just heat. There's also this concept of work. Now, that becomes our first major idea in thermodynamics. And that is that the transfer of energy can be seen from really 2 major perspectives. From the perspective of heat transfer or the perspective of work. Now, from our studies of mechanics so far, and probably some chemistry, we know that heat is measured in joules most of the time as an SI unit, and work is measured in joules as well. So energy as a whole is measured in joules. And I think what really gives us a good understanding of the connection between these things is that the units are the same. They're really showing us that work and heat are transfers of energy that are both connected by the fact that they are energy, but they are very distinct. And we will get into that in a lot of detail in this series. Now, one of the main things we need to focus on is that work can be seen as a mechanical transfer of energy. A mechanical transfer of energy is oftentimes described as an orderly transfer of energy. Now, we've talked about work from many different standpoints already in our studies of physics, and here we're going to use a lot of those same concepts and expand them. Now, heat is often seen as a random transfer of energy, which is in contrast to the ordered transfer of energy that we see in our understanding of work. Now, we are going to find out what causes a heat transfer versus work being done. And that's going to be one of the major distinguishing factors between the two that we will uncover and unfold in the next few videos. So with a very rudimentary definition and contrast of work and heat, one being the ordered transfer of energy, the other being a more random transfer of energy, we're going to try to relate the two to one another from this perspective. Let's say that I have a system of molecules. Let's call it a gas, for instance. We have a gas in, let's say, a balloon. So that could be just air. Now, air is made up of a lot of molecules, and we know from our studies in chemistry and biology that these air molecules are moving to fill the space. They're pushing on the surroundings of the balloon and therefore holding the balloon walls up. Now, what's pushing on the outside of the balloon, we've kind of talked about already in the fluid mechanics little mini section, and that was the atmospheric pressure. Now, what we're going to focus on is really just this interior system, and the boundaries of the system are the balloon sides. Now, we're going to describe this internal energy of the system. So in very basic terms right now, we're going to describe the state that the system is in. Now, this is a very important word that we're going to use many times and to help categorize different things in thermodynamics. We describe the state that a system is in, and then we describe a process by which a system changes its state. Now, we're not only talking about like states of matter or phases of matter, we're just talking about a state, any given state. So while this air in the balloon is still a gas, it can exist in many different states as a gas. It can also exist in many different states as a liquid if we're able to compress it enough. Now, what we want to focus on is that the states can be changed by processes. And if you're thinking already ahead to this idea of work and energy and heat, you can see that work and heat are processes by which we can change the state of a system. And that's a major fundamental idea that we really need to internalize as we travel through this area of thermodynamics. So as the state is changed by a process being work or heat exchange, we see that the internal energy of the system changes as a result of a process having occurred. So this allows us to write a very simple, or apparently simple, equation that is known as the first law of thermodynamics. Now, this is a statement oftentimes attributed to conservation of energy, and it is. It's basically saying you can't destroy energy, you can't create energy in a system without actually having put something in the system. So energy can't increase in the system without me actually doing something to the system. But what it says in very basic terms is that if I do work on a system, so in other words, I'm transferring work mechanically to the system, and if I exchange heat into or out of the system through a random transfer of energy, both of those two things together can account for the change in the internal energy of the system. So this is a pretty broad term right now, and we're going to, in the subsequent videos, really pin it down and understand what is internal energy actually. What is it a measure of? What is work a measure of in terms of thermodynamics? And then we'll unpack more about heat as well. So the final topic I want to just explore a little bit in this video is the idea of the kinetic theory. Now, kinetic theory, sometimes known as kinetic molecular theory, really for us right now, we're just going to start with a very basic idea and we will expand on it through the next several videos. Kinetic theory basically says systems are made up of particles, and the particles, as the word kinetic indicates, the particles are moving. Now, even in a solid, the particles are moving, but they may not be moving in the same way that they are in a liquid versus a gas versus a plasma. The particles in the system from the kinetic molecular theory can be described in many different ways. We could describe the macro state of the system. This important term uses words like pressure, volume, temperature, and internal energy to describe the overall look of the system, if you will. Now, as we talked about a few minutes ago, when a process is done to the system, so heat is exchanged or work is done to the system's macro state will often change. So in other words, if I have my balloon example again, if I compress the balloon, I know that the molecules become closer together and the pressure increases in the balloon. That's something that most people would say from common knowledge is true. Now, if I blow more air into the balloon, I'm once again doing some sort of process to the balloon, some energy exchange. And in that case, I'm actually changing the macro state as well. Now, what is not as apparent as the change in macro state, which is very easy to see most of the time, is that there are many little microstates that can describe that one macro state. In other words, if I'm tracking, let's call him Bob the particle, if I'm tracking Bob through this system, Bob can be in many different places within the system, and I still measure the same, let's say, pressure. At another random snapshot in time, Bob might be over here on the left, and I might read a pressure in the system of, let's say, 100 pascals. In a snapshot a few seconds later, Bob might be over here on the top right. And we might still measure the same measurement for the pressure, 100 pascals. So in other words, what I'm getting at is that there can be many different microstates that make up an overall macrostate of a system. Now, I introduce all these terms in this video because as we go through the next part of thermodynamics, we're going to take a look at the definitions of temperature, what the difference of temperature and heat are. We're also going to take a look at how heat engines, function in basic senses. We're going to get into a lot of these details, but the most important thing is to think through the process from the perspectives of working heat as being processes that change the macro state or the state of a system by many different microstates. If you think of it in those terms, thermodynamics will be a whole new world to you and something very interesting and actually a lot more manageable than if you just look at it from a very basic or distant standpoint. So I leave you with this challenge. Go to the PhET simulation at phet.colorado.edu and try to figure out if you can come up with a definition of temperature that includes several of the definitions and ideas that were presented in this introduction. And I'll see you at the next video to discuss those findings.